Welcome to All in All.
Great to be diving in again.
Today we're embarking on a pretty deep dive into a world that has fascinated us, sparked, passionate debates, and truly reshaped our cosmic understanding. Pluto. We've got a formidable stack of sources for this one. I mean, everything from cutting-edge scientific papers detailing its very formation to surprising revelations about its dynamic atmosphere, and of course that whole spirited debate that surrounded its reclassification.
Yeah, that was something. Our mission today is to thoroughly explore Pluto's profound origins, unravel its remarkable evolution over billions of years, understand its broader significance to planetary science,
Right.
its undeniable impact on our understanding of the cosmos, and its practical relevance to scientific inquiry and, well, beyond.
So get ready to uncover some truly surprising facts, folks, and gain a really well-informed, up-to-the-minute perspective on this distant, captivating world.
Absolutely. Let's jump in.
Okay, let's unpack this. We're starting at the very beginning, a truly primordial tale, with the birth of a world and its companions focusing on Pluto's origin. The formation of the Pluto system, especially that unusual Pluto-Charon binary, it isn't just one simple story, is it?
No, not at all. It's more like a cosmic detective case with several compelling hypotheses, several leads to follow.
So where do we start? The classic theory.
Yeah, let's start there. For decades, one of the leading explanations has been the giant impact hypothesis. You've probably heard of this one. This theory suggests that Pluto and its largest moon, Charon, formed after
So, a catastrophic event, but way out there in the cold. What kind of impact are we talking about here? For Charon to end up in a stable orbit? I mean, not just becoming a messy pile of rubble or, bouncing off into space.
That's the crucial detail, yeah. And it really sets this impact apart. For Charon to be successfully captured into orbit, rather than just bouncing away or fully merging into one body, this collision would have required a very specific and remarkably low collision velocity.
Low velocity, okay.
Yeah, really low. We're talking about a relative velocity at a large separation of less than 0.7 kilometers per second.
Wow.
To give you a sense of just how precise that is, it's within only 20% of the mutual escape velocity of the two bodies, basically. Just barely enough speed for them to kind of connect without flying completely apart or merging entirely. A cosmic nudge, almost.
That sounds incredibly specific, like hitting a cosmic bullseye at just the right gentle speed. Does that tight requirement actually fit with what we imagine the early solar system was like? Was it calmer back then?
It absolutely does. That's the beauty of it. This low velocity requirement aligns perfectly with conditions we think existed in the primordial epoch, that incredibly chaotic but maybe locally calmer early period of our solar system's formation.
Okay.
Specifically, it suggests the impact happened before Neptune's migration dynamically excited or, stirred up the trans-Neptunian region.
Ah, right, before Neptune went wandering and shook everything up.
Exactly. Back then, velocities among these large bodies would have been much lower than what we see in the sort of scattered Kuiper belt today.
Wow.
So the timing works. And this model also successfully accounts for some of Pluto's most peculiar features.
Like what?
Like its surprisingly high angular momentum, how fast it spins, and its overall rotational energy and its high obliquity, which is that significant 57-degree tilt of its rotation axis relative to its orbit.
57 degrees, yeah, that's a big tilt.
It is, and those are tough characteristics for other theories to explain easily. The giant impact gives you a way to get that energy and that tilt from the collision itself.
Okay, so tick some major boxes. But as with any scientific theory, I'm guessing it's not without its challenges, right? What are the tricky bits with the giant impact hypothesis?
You're right, no theory is perfect, especially when you're talking about events billions of years ago. One significant difficulty is explaining how Charon maintained its predicted orbital eccentricity, how oval its orbit is during its subsequent evolution after the impact. Getting that right requires a very specific and narrow range of tidal parameters, the gravitational forces between Pluto and Charon as they settled down. And those parameters are, well, hard to pin down with certainty.
Okay, so the orbital details are a bit fiddly. Anything else?
Yeah, another thing. When scientists run numerical integrations, these sophisticated computer simulations that include Pluto's oblateness, its slight flattening due to spin.
It's J2, right?
Exactly, it's J2. When they factor that in, those simulations tend to destabilize resonant capture models for the smaller moons, like Nix, Styx, Hydra, and Kerberos.
Resonant capture. So how they got locked into their current orbits.
Right. These models describe how moons can get locked into stable, synchronized orbits. But if Pluto's slightly non-spherical shape, its J2 is factored in, these models often make the orbits of those tiny outer moons dynamically unstable within the giant impact framework.
So the impact might explain Charon, but mess up the orbits of the little guys.
It implies that if such an instability occurred, maybe the debris from the impact had to reform a second generation of satellites later on, which, adds another layer of complexity to the story. It's not impossible, but it's less straightforward.
Okay, so the giant impact theory. Good for the big binary, maybe struggles a bit with the smaller family of moons unless there's some kind of reformation event. Fascinating. But there's another intriguing idea out there. The co-accretion scenario. This one sounds, well, less violent, like they didn't collide, but rather grew up together, side by side.
That's a good way to put it. Yeah, a more gentle formation story. This scenario was actually dismissed in older studies, primarily because it couldn't easily explain Pluto's high obliquity or that high angular momentum we mentioned.
Right, the things that giant impact does explain well.
Exactly. But a more modern understanding of co-accretion has emerged, quite distinct from those older studies, especially ones about how Earth's moon didn't form. It paints a picture of a potentially more plausible, gradual formation.
What changed? What's the modern part of this co-accretion theory, and how does it tackle those earlier challenges?
Well, the key lies in new developments in understanding planetesimal formation, the process by which tiny dust grains in the early solar nebula clump together to form kilometer-sized building blocks of planets.
Okay.
Specifically, something called gravitational collapse induced by the streaming instability. It's a bit of a mouthful.
Streaming instability.
Right.
What does that mean in practice?
Imagine a dense cloud of pebbles and gas in the early solar system disk. The streaming instability causes these particles to rapidly clump together locally, much faster than traditional accretion, and then collapse under their own gravity.
Okay, a rapid collapse.
Yes. And as such, a collapsing clump of mass undergoes this self-gravity-driven collapse. Its high specific angular momentum, again, think of its rotational energy, its spin can actually prevent it from forming just a single body.
So the spin keeps it from becoming one
But
blob.
instead, that rapid internal spin can cause it to fission, basically, to yield a high angular momentum binary system, and potentially one with a high obliquity and a mass ratio very similar to that of Pluto-Charon. It's like a cosmic pirouette where the spin causes a split rather than a consolidation into one.
That makes a lot of sense for how any binaries could form from a collapsing cloud, especially smaller ones. But does it fully account for something as, well, massive as Pluto and Charon specifically? Are they too big for this?
That's potentially a limitation, yes. Direct formation of a binary as massive as Pluto-Charon by this specific streaming instability process is considered, well, unlikely by some models.
Why is that?
The challenge is that such large mass concentrations, the kind you'd need to form Pluto and Charon directly, tend to fragment into smaller pieces before the collapse is complete. It might be hard to get two substantial, distinct bodies like Pluto and Charon in one go this way.
Okay, so a scaling problem maybe? What about their composition? If they form together like this, shouldn't they be identical twins, chemically speaking?
That's another point. You'd expect them to have very similar compositions if they form directly from the same collapsing clump. And they are similar, but not identical. Their bulk density difference is small, only about 8%. But that slight difference still hints that maybe they didn't form from the exact same initial batch of material, or maybe something happened after formation.
So a slight compositional mismatch and a challenge with the sheer scale. But you mentioned earlier there was an enticing feature of this co-accretion idea, something that solves a problem for the other theories.
Yes, this is where it gets really interesting, and why it's still a contender. A major strength of this co-accretion scenario is its potential to naturally explain the formation, and crucially, the stable, nearly circular orbits of Pluto's small moons, Nix, Styx, Hydra, and Kerberos.
Oh, the little guys again. How does co-accretion help with them?
In this model, material to form these moons could have been initially placed near their current orbits during the original collapse process itself. They could have formed alongside Pluto and Charon, or from a circumplanetary disk. This eliminates the need for complex outward migration models that you often need in the impact scenarios.
Right, because in the giant impact model, explaining how these tiny moons ended up in their current, surprisingly stable and nearly circular orbits way out there is quite a puzzle, isn't it?
It is. Getting them out there and keeping them in those nice ordered orbits after a massive collision is tricky. Co-accretion offers a potentially cleaner solution for the whole system architecture.
That is a neat solution for the smaller moons. Okay, theory number 3.
Yeah.
And this one has a truly evocative name, the kiss and capture theory. That name alone just makes you want to know more. What's the story here?
It's quite vivid, isn't it? This is a more recent simulation proposing a unique kiss and capture process for Charon's formation, and it adds a crucial new element to our thinking about cosmic collisions, something often overlooked before.
Which is?
The role of material strength, how strong the actual stuff is that these bodies are made of.
Material strength. How does that change the game in a cosmic collision?
Right.
We often think of planets and moons as just massive collections of rock or ice, not necessarily having strengths like, say, steel on Earth.
That's a great question, and it's absolutely key to this theory. When Proto-Charon struck Proto-Pluto in these simulations, the material strength of their ice-rock mixture, essentially, how resistant their frozen and rocky components were to breaking or deforming under pressure, played a truly crucial role. The simulations showed that friction within this icy, rocky material helped to distribute the impact's momentum in a specific way. Instead of a clean bounce or a complete merging, this internal friction caused the two objects to become physically connected, almost, well, entangled, for tens of hours. That's the kiss part. They sort of grazed, stuck together briefly.
Tens of hours, wow.
Yeah. And then, crucially, the strength of the ice prevented them from fully merging into one larger body during that time. It gave them just enough rigidity to resist complete collapse. This led to their eventual physical separation, but importantly, remaining in a close, captured orbit around each other. That's the capture.
So they literally got stuck together for a while because of friction and material strength before orbital mechanics took over and settled them into their binary dance. That's wild.
It is a pretty wild idea, yeah. And very different from just a simple billiard ball collision.
And you mentioned this scenario could also potentially explain Pluto's other smaller moons, the whole family again.
Yes, that's another incredibly exciting aspect of this model. This kiss and capture scenario, because it's still a significant impact, naturally produced enough collisional debris material ejected from the impact zone to potentially form Pluto's minor moons: Nix, Styx, Hydra, and Kerberos.
So the debris cloud could coalesce into the moons.
That's the idea. While the simulations weren't quite powerful enough back then to model these tiny moons forming directly from the debris cloud in detail, the amount and distribution of ejected materials seemed about right. It fits the general picture of having enough mass scattered in a way that could lead to their formation over time.
So this theory tackles both the main binary and potentially the smaller, mysterious moons. And it might not just be a one-off Pluto story. This could be common out there.
Exactly. That's a key implication. This kiss and capture mechanism, because it depends on the material strength of icy bodies, might actually be a common process for forming other icy binary objects throughout the Kuiper Belt.
Like Orcus and Vanth. I remember reading about them.
Precisely. Researchers have successfully modeled the formation of Orcus and Vanth, another similar pair of icy bodies out there, using the same kiss and capture mechanism. This suggests that Pluto and Charon might not be cosmic anomalies, but rather a prime example of a common binary formation process for icy worlds.
Fascinating. But wait, there was a catch you mentioned earlier, connecting this to a possible ocean.
Ah, yes, the plot thickens. Here's a fascinating counterpoint, a way we might test this theory. Definitive evidence for a substantial subsurface ocean on Pluto today would actually argue against the kiss and capture scenario as currently modeled.
Why? How does an ocean argue against this impact model?
The dynamics of the kiss and capture impact, being more of a grazing collision perhaps, might imply a colder Proto-Pluto initially compared to a direct high-energy giant impact. It might not generate and retain enough heat deep inside to sustain a large liquid ocean for billions of years. So finding a big ocean now might suggest Pluto started hotter, perhaps favoring a different impact scenario or the co-accretion model.
That's a fantastic link. How theories of formation, happening billions of years ago, can be constrained or even tested by looking at the internal conditions today. It's a true feedback loop in science.
It really is. What we see now tells us about the beginning.
Speaking of internal conditions, let's turn our attention inward to Pluto's fiery interior, unveiling early differentiation and the hidden ocean. It's still kind of hard to imagine a fiery interior for an icy world so far from the sun, where surface temperatures are, what, minus 230 Celsius?
It is counterintuitive, isn't it? But fiery here doesn't mean molten rock like Earth's mantle. It refers to internal heat, and that's a testament to the power of internal processes, even in the deep freeze of the outer solar system. Pluto's bulk composition is roughly 2/3 rock and 1/3 ice, remember?
Right. Mostly rock, surprisingly.
Yeah. Its rocky core is likely surrounded by a thick mantle of water ice. Now, the primary heat source for the deep interior of isolated bodies like Pluto isn't the distant sun, but rather the slow, steady decay of short and long-lived radionuclides within the rocks.
Radioactive decay, like uranium and thorium.
Exactly. Elements like uranium, thorium, and potassium-40 trapped inside Pluto when it formed. Their radioactive decay releases heat, slowly but surely, over billions of years. This internal radioactivity provides enough heat to warm the interior rocks close to their melting point, potentially sustaining geological activity and, crucially, warming the overlying ice layers.
So it's cooking itself from the inside out, in a way. A slow-burn nuclear furnace deep inside. But for differentiation, that process where denser materials sink to the center, the rock settling toward the core, the ice has to melt first, right? Rock can't sink through solid ice easily.
Precisely. That's the key step. For pure water ice, it melts around 273 Kelvin, which is 0 degrees Celsius. That's still incredibly cold for us, but maybe too warm for just radioactive heating alone to achieve easily throughout a large volume.
Okay.
However, here's where Pluto's unique chemistry likely comes into play. Pluto's ice probably isn't pure water ice. It likely contains small, maybe just percent-level amounts of ammonia and H3.
Ammonia. Like in cleaning products, how does that help?
Even these tiny amounts of ammonia act like a potent antifreeze. They significantly depress the ice's solidus. That's the temperature at which the first bit of melt appears down to a much, much lower 176 Kelvin.
176 Kelvin. What's that in Celsius?
That's about minus 97 degrees Celsius or minus 143 degrees Fahrenheit. Still frigid by our standards, but crucially, it's a temperature much more achievable through internal radioactive heating alone. It makes the presence, or at least the past presence, of liquid water far more plausible.
Wow, so ammonia makes a huge difference. And once melting starts,
Once even a little melting starts, the ice viscosity, its resistance to flow, plummets by orders of magnitude, becomes much weaker, allowing the denser rock particles to finally settle down through the slushy mix towards the center, driving differentiation.
that's a critical detail, that ammonia acting as a cosmic antifreeze. Okay, and the timing of this heating matters too, I gather. The amount of heat from Pluto's formation itself, the accretional heating, plays a huge role in its internal history.
It absolutely does. How Pluto formed, whether quickly and violently, retaining a lot of impact heat, or more slowly and gently, can lead to very different thermal evolutions and internal structures early on. Let's think about two distinct scenarios for that initial burst of heat from formation, which we call accretional heating, the energy from all those impacts building the planet. We represent the fraction retained by H.
Okay, scenario one, a cooler start.
Let's say there was moderate retention of accretional kinetic energy, maybe H was 0.2, so 20% was retained. And maybe Pluto's progenitor formed relatively early, say about 7 million years after CAIs. Those are calcium-aluminum-rich inclusions, the oldest solids in our solar system, marking time 0.
Right.
In that case, differentiation would likely have started in the outer regions first, within less than 10 million years, as radioactive heat built up. This would have created an outer ice shell overlying a developing water-ammonia ocean. Temperatures would have been cooler, deeper down initially, with the body warming from the inside out over time as the core heated.
Okay, warming from the inside out. And what if Pluto formed with more initial heat, say from bigger, more energetic impacts, a hotter start?
Right. For larger planetesimal impacts, maybe 40% or more energy retention, H equals 0.4 or higher, it could have resulted in the outer regions starting out partially or even fully melted right from the outset, a hot start.
So melted from the beginning almost.
Almost. In this more energetic scenario, differentiation would have proceeded differently from the outside in. The rock settles out first where it's already melted near the surface.
Outside in. That sounds weird. What kind of structure does that create?
It leads to a fascinating but temporary structure, an undifferentiated central region, still a mix of rock and ice, surrounded by a denser rocky layer that has already settled out from the initially melted outer parts. This rocky layer, sitting on top of less dense material, would be gravitationally unstable, naturally wanting to sink, and all of this enveloped by a liquid water ammonia ocean and a thin outer ice shell.
So rock settling from the outside, rather than the inside sinking down. How long would that process take, and what does it mean for having a sustained ocean early on?
Differentiation by rock settling in melted ice in this hot start scenario could be complete surprisingly quickly, maybe within about 30 million years. And here's a crucial point for habitability discussions. This more significant initial accretional heat could sustain a substantial ocean, potentially more than 100 kilometers thick, for at least 60 million years, maybe longer.
60 million years of a liquid ocean early on. That's significant.
Very significant. As this ocean eventually refroze over hundreds of millions or even billions of years, the structure would change. It would transition from having a thin, conductive ice shell above a vigorously convective ocean to a thick, convective ice shell above perhaps just a thin remaining liquid layer near the core. And paradoxically, this refreezing process could actually cause the deep core to warm up significantly later on due to insulation.
Wow. It really shows how sensitive the internal structure even today could be to when that binary forming impact happened relative to the progenitor's own accretion and heating. The early history directly dictates the deep hidden present.
Exactly. The first few million years set the stage for billions to follow.
Incredible stuff. Thinking about the deep past shaping Pluto's interior today, potentially hiding an ocean.
Oh.
Okay, moving on from its very birth and deep interior, let's explore a world of constant change, looking at Pluto's evolution over time. First up, its atmosphere. A shifting veil. It's famously thin, right? What's it made of and what's going on up there?
It is very thin, yes, incredibly tenuous compared to Earth's, and cold. It's predominantly nitrogen, making up about 99% of it.
Almost pure nitrogen.
Pretty much. Then there's methane, CH4, making up about 0.25%, and a whiff of carbon monoxide, COO, around 0.05%. But it's not just a simple static gas mix. There's chemistry happening.
Chemistry. Driven by what?
Under the influence of high-energy cosmic radiation from space galactic cosmic rays and solar UV light, these simple gases react. They form more complex, non-volatile compounds like ethane, ethylene, acetylene, other heavier hydrocarbons, and also nitriles, including hydrogen cyanide, HCN.
So sunlight and radiation are breaking down the simple stuff and making more complex molecules.
Exactly. These heavier compounds then slowly precipitate or snow out onto the surface, forming thin layers, and they likely include tholins.
Tholins. Those are the reddish-brown organic gunk things, right? Like on Titan.
That's them. Complex organic molecules formed by radiation processing. They're thought to be responsible for Pluto's characteristic brownish or reddish colors in many areas. And New Horizons didn't just see the color on the surface, it captured stunning images of distinct blue haze layers suspended high in its atmosphere, likely made of these same complex particles scattering sunlight.
Blue haze and red tholins.
Yeah.
Quite the palette.
So it's not just a simple gas mix, there's a whole chemical factory at work up there. What's the atmosphere's temperature profile like, given how cold Pluto is overall? Does it just get colder the higher you go?
Actually, no, it's more interesting than that. It exhibits a fascinating and unexpected temperature profile. It actually warms up at certain altitudes.
Warms up? How?
Yeah, it reaches a temperature maximum of about 100 to 110 Kelvin. That's about minus 173 to minus 163 degrees Celsius at a height of 20 to 40 kilometers above the surface. Methane absorption of sunlight might play a role here.
So a warmer layer high up. And then above that.
Above that warmer bulge, the temperature slowly decreases again, eventually stabilizing at approximately 80 Kelvin or minus 193 Celsius above 200 kilometers.
Still incredibly cold by Earth standards, but it's remarkably stable, you said.
Mm-hmm.
Are there big variations in temperature like we see on Earth with day-night cycles or seasons or different latitudes? Surprisingly, no. Not much variation in the upper atmosphere. Unlike Earth, Pluto's upper atmospheric temperature shows no noticeable temporal changes, no significant differences between latitudes, or even morning-evening variations. It remains remarkably constant around that 100 Kelvin mark, at least based on the New Horizons flyby data and stellar occultations.
They're so stable.
This consistency is actually in line with theoretical predictions of fast atmospheric mixing. Winds and currents, even in such a thin atmosphere, seem to quickly distribute heat horizontally, evening out temperature differences across the globe quite efficiently.
Okay, so it's mostly uniform, but you hinted at some dynamism, little ripples.
Right. While it's globally quite uniform, New Horizons did detect small vertical heterogeneities, tiny fluctuations of about 0.5 to 0.8 Kelvin over just a few kilometers vertically. These likely indicate localized atmospheric gravity waves or maybe small pockets of turbulence, possibly related to convection rising from the surface, or subtle winds interacting with the terrain. So it's not completely stagnant. There are hints of weather, albeit very subtle.
Little atmospheric waves.
Yeah.
Cool. Okay, what about the atmospheric pressure itself, the overall amount of atmosphere? Has that been stable over time? I seem to recall hearing about some surprising changes recently.
Not stable at all, and this is where things get particularly interesting and dynamic. We monitor Pluto's atmosphere using ground-based observations of stellar occultations.
Right, where Pluto passes in front of a distant star.
Exactly. We watch how the star's light dims as it passes through Pluto's atmosphere. It's like taking a slice, a profile, through the atmosphere from Earth. We've been doing this since the 1980s, building up a long-term record.
And what has that record shown?
Well, for a while, the pressure seemed to be increasing as Pluto moved closer to the Sun in its orbit. But then, in 2019, a particularly well-observed occultation revealed an unexpected, quite dramatic drop in atmospheric pressure, about 20% down since 2016, and this finding was confirmed by other data from 2018.
A 20% drop in just a few years. That seems really fast. Does that mean Pluto is just rapidly losing its atmosphere into space? Is it just, evaporating away?
It is losing its atmosphere, yes. But, and this is crucial, the rate is far, far lower than scientists initially thought before New Horizons got there. That was one of the mission's biggest surprises.
How much lower? What were the old estimates?
Early estimates, pre-New Horizons, based on modeling and limited data, suggested a very high rate of atmospheric loss, something like a 1027 to 10 to 1,000 hydrogen molecules escaping every second.
Okay, that sounds like a huge number. What does that mean in practical terms?
It was equivalent to losing hundreds of meters, maybe even several kilometers, of volatile ices like nitrogen and methane from Pluto's surface over the solar system's lifetime. If that were true, Pluto's atmosphere should have long since vanished, or at least been dramatically depleted compared to what we see. It didn't quite add up.
Right, that sounds like a truly significant loss, implying a very transient atmosphere.
Yeah.
So what did New Horizons actually measure? What was the reality?
New Horizons data, particularly from its instruments designed to study the atmosphere and its escape, drastically revised this loss rate downward by at least 4 orders of magnitude.
4 orders, so 10,000 times less.
Yes. Instead of those enormous numbers, Pluto is currently losing only about 1 by 1,023 nitrogen molecules and maybe 5 by 1,025 methane molecules per second. Methane escapes more easily.
Okay, still sounds like a lot, but much less than before. What does that translate to over cosmic time?
To put that revised rate into perspective, over the solar system's entire 4.5 billion-year lifetime, this equates to a loss of only several centimeters of nitrogen ice and perhaps several dozen meters of methane ice from its surface.
Centimeters, wait, from kilometers down to centimeters of nitrogen ice lost?
Yes,
That's almost nothing.
exactly. It's a negligible amount. This isn't just tweaking a number. It completely overturned our prior assumptions about atmospheric escape at Pluto. It means Pluto isn't rapidly wasting away. Its atmosphere, thin as it is surprisingly stable in terms of loss to space. It suggests a much more enduring geological and atmospheric cycle where surface ices sublimate to replenish the atmosphere than we ever imagined.
So the recent 20% pressure drop isn't about escape then? What's causing that?
That pressure drop is almost certainly due to Pluto's current orbital position. It passed perihelion, its closest point to the Sun, back in 1989, and is now moving farther away on its long elliptical orbit. As it gets farther and colder, its main atmospheric component, nitrogen ice on the surface, starts to condense and freeze back onto the surface more readily. It's like frost forming. So the gas atmosphere above gets thinner as the nitrogen freezes out. It's a seasonal effect on a grand, decades-long scale.
Ah, okay. So it's breathing in and out with its seasons, but not really leaking away into space much at all? That makes sense. How does this thin escaping atmosphere interact with the solar wind way out there?
Even though the escape rate is low, some molecules do escape with high enough velocity. These then get ionized by solar ultraviolet radiation, becoming charged particles.
Ions, right.
Yes. These ions form an obstacle to the solar wind, that constant stream of charged particles flowing out from our sun. This obstacle then slows and diverts the solar wind around Pluto, potentially creating a weak shock wave upstream, much like a boat creates a wake as it moves through water.
Did New Horizons see that interaction?
It did. The solar wind around Pluto, or SWAP, instrument on New Horizons, made the first ever direct measurements of this region, specifically detecting the low-energy atmospheric ions being picked up by the solar wind shortly after the spacecraft's closest approach in 2015. These direct measurements are vital for understanding how even these tenuous atmospheres in the outer solar system interact with the broader solar environment and evolve over time.
That's amazing, getting direct measurements of that interaction so incredibly far from Earth.
Okay, beyond the atmosphere, New Horizons also just totally transformed our understanding of Pluto's surface itself. Let's talk about surface resurfacing and internal activity, a surprisingly active world. Because before New Horizons, I think most scientists expected Pluto to be, well, kind of boring geologically, a frozen, cratered, maybe dead world.
Indeed, that was the prevailing wisdom, just an ancient, icy, battered sphere. But the 2015 New Horizons flyby completely shattered that picture. It revealed an unexpectedly diverse, dynamic, and geologically active world. The images were simply breathtaking.
What do they show? They showcased vast, smooth plains of solid nitrogen ice, like Sputnik Planitia, towering mountains made not of rock, but of water ice acting as bedrock, deep, rift valleys suggesting ancient tectonic activity or stresses, and evidence of active glaciers flowing across the surface. It was anything but a static, ancient snowball. It looked young, dynamic.
And one of the most striking discoveries, maybe the most surprising, had to be widespread evidence of cryovolcanism. Ice volcanoes. What exactly is that, and how does it manifest on Pluto?
Cryovolcanism is literally ice volcanism. Instead of molten rock erupting like on Earth, you have icy materials, mixtures of water, ammonia, methane, nitrogen, perhaps other volatiles erupting onto the surface from the interior.
Okay.
On Pluto, New Horizons revealed compelling evidence for this kind of large-scale cryovolcanic resurfacing in several areas, strongly indicating an internally active body, something we simply hadn't anticipated for such a small, cold world. And two features in particular stand out as likely candidates for massive cryovolcanoes: Wright Mons and Picard Mons.
Wright Mons and Picard Mons. Tell us about them. Give us a sense of their scale and what makes them look like volcanoes, albeit icy ones.
They are huge and morphologically very complex, unlike anything else we've seen quite like them. Wright Mons, for instance, stands approximately 4 to 5 kilometers high. That's about 2.5 to 3 miles, taller than many mountains on Earth, and spans about 150 kilometers or 93 miles across its base.
Oh, wow, that's enormous.
It is. Its estimated volume is similar to Earth's Mauna Loa, one of the largest shield volcanoes on our planet. Picard Mons nearby is even larger, potentially reaching about 7 kilometers high at its tallest points and stretching 225 kilometers wide.
Bigger than Mauna Loa, potentially. Made of ice.
In volume, yes, possibly. And what makes them look cryovolcanic beyond their sheer size and shape are the peculiar large, irregular depressions at their summits. Some have sharp, flat edges. These don't look like impact craters formed by something hitting Pluto.
So what could they be? Calderas, like on Earth volcanoes?
Possibly something analogous, yeah. They might be formed by material welling up from beneath the surface, creating a kind of broad ice dome that then partially collapses as the eruption wanes or shifts. Or perhaps they result from localized collapse as the underlying magma chamber, in this case, a reservoir of slushy cryomagma, empties or moves.
So it's maybe not just a single massive eruption, but perhaps a complex ongoing process. Maybe multiple vents building up these features over time, like shield volcanoes on Earth, but with icy lava.
That's precisely what a detailed examination of the New Horizons imaging and compositional data suggests. These massive cryovolcanic constructs likely didn't form from a single giant subsurface source erupting all at once. It's more probable they form from multiple subsurface sources or vents activating over time below them, with different icy rises and flows merging together to create these grand, sprawling features.
That sounds more plausible than one giant iceberg.
It does. And this multiple source scenario elegantly avoids the need for enormous single collapse events to explain those giant summit depressions. It suggests a more prolonged, perhaps episodic, and distributed process of icy material upwelling from Pluto's interior. Still active today, we don't know for sure, but certainly geologically recent.
What can the surface composition on these features tell us? Does the chemistry give us clues about the cryovolcanism and Pluto's deeper history?
Oh, absolutely. The compositional clues mapped by New Horizons are crucial. For example, methane-rich ice seems to be more prevalent at higher elevations on Pluto generally, including on these mons. This suggests it might be a thin, volatile surface layer deposited from the atmosphere, like methane frost or snow, blanketing the underlying terrain.
Okay, so methane snow on the peaks. What about other areas?
Conversely, darker, lower albedo patches, areas that are presumably slightly warmer where the volatile methane ice is unstable and has sublimated away, show stronger spectral signals of the underlying water ice bedrock. And this water ice often appears mixed with that dark, reddish organic material, the tholins we discussed earlier, perhaps brought up from the interior or created on the surface.
And the colors vary too, right? Not just red and white.
Yes, the subtle but distinct color variations across different regions, from redder terrains to less red or more neutral terrains, even within these cryovolcanic areas, suggest different things. Maybe these areas were emplaced at different times, tapping into slightly different source reservoirs in the subsurface, or perhaps experiencing variations in the extrusion process itself, how the icy material erupted. It's like reading geological history written in color and chemistry.
So Pluto is this surprisingly dynamic place shaped by both atmospheric cycles like nitrogen freezing out and deep internal heat driving cryovolcanoes and maybe maintaining an ocean. It's far more complex than we ever thought.
Absolutely, a whole new world revealed.
Now let's explore Pluto's peculiar orbit and system of moons, a dance in the outer solar system. Its orbit around the Sun is certainly unique compared to the classical planets. It's almost a cosmic outlier in its path.
It is indeed very peculiar. For starters, Pluto takes about 248 Earth years to complete a single orbit around the Sun.
248 years.
Yeah, think about that. From its discovery in 1930, it hadn't even completed one full Pluto year by the time it was reclassified in 2006, and it won't complete that first observed orbit until the year 2178.
Wow. So human observation of Pluto has, so far, only ever captured a fraction rather than half of its grand cosmic journey around the Sun.
That's right. We've only seen it through part of its year.
And its orbit isn't just long, it's quite different in shape and tilt from what we typically think of for the major planets, which all lie pretty much on the same flat plane, right?
Yeah. Yes, very different. Unlike the nearly circular and relatively flat orbits of the classical planets, which all orbit more or less in the same plane as the Earth's orbit, called the ecliptic Pluto's orbit, is highly elliptical. It's quite elongated, like a stretched circle.
So its distance from the Sun changes a lot.
Significantly. And it's also significantly tilted. We're talking about an orbital inclination, a tilt, about 17 degrees relative to the ecliptic plane. Oh, wait, I think I misspoke earlier about the 57 degrees. That's its axial tilt, its obliquity. Its orbital tilt is 17 degrees. Still quite high compared to most planets.
Okay, 17 degrees orbital tilt, 57 degrees axial tilt. Got it. Still pretty tilted orbitally. And didn't you also mention it spins backwards?
Yes, it also exhibits retrograde rotation, spinning from east to west on its axis, similar only to Venus and Uranus among the major planets. So its day goes the wrong way, and it's tilted way over on its side as it orbits, another layer of peculiarity.
Now, I remember hearing that because of its highly elliptical path, Pluto's orbit actually brings it closer to the Sun than Neptune at times. Is that right? Does that mean there's a risk of them colliding, or at least having a dangerously close encounter someday?
That's a very common question, and it's true. Its orbit crosses Neptune's path. Due to its elliptical orbit, Pluto's path occasionally brings it closer to the Sun than Neptune. This last happened for about 20 years, from 1979 to 1999.
So it was the eighth planet for a while, technically?
In terms of distance, yes. And it won't happen again until around the year 2227. However, and this is the crucial part, despite their orbits crossing, there's no risk of collision. Pluto and Neptune are locked in a remarkably stable 3.2 orbital resonance.
The 3.2 resonance, what does that mean exactly?
It means that for every 3 times Neptune completes an orbit around the Sun, Pluto completes exactly 2 orbits. This precise gravitational lock, this repeating pattern, ensures they are never in the same place, or even close to the same place at the same time when their orbits cross. Neptune is always far away when Pluto is near its crossing point.
So they're choreographed.
Perfectly choreographed by gravity. It prevents any collisions and maintains a long-term, stable dance. It's a beautiful example of how complex gravitational interactions in the solar system can create long-term order out of seemingly chaotic orbits.
That's a fascinating cosmic dance they perform. And of course, Pluto isn't alone out there. It has its own family of moons, the most prominent being Charon, its giant companion.
It does, and it's a surprisingly complex little system for its size. Pluto has 5 known moons discovered over several decades: Charon, Nix, Hydra, Kerberos, and Styx.
Charon being the big one.
By far. Charon, discovered back in 1978, is the largest and innermost moon. It's about half the size of Pluto itself, and remarkably, about 12% of Pluto's mass.
12%. That's huge for a moon. Our moon is only about 1% of Earth's mass.
Exactly. This makes Charon the largest satellite relative to its primary body in our entire solar system. It truly earns them the moniker of a double planet system.
Double planet, because they orbit each other.
Well,
Partly because of the size ratio, but also because Pluto and Charon share a common center of gravity, the barycenter, that actually lies outside Pluto's surface, in the space between them. They truly orbit around this external point together.
Ah, okay. That's different from Earth and Moon, where the barycenter is inside Earth.
Right. And they're also tidally locked, meaning they always show the same face to each other, just like our moon does to Earth. If you stood on Pluto, you'd only ever see one side of Charon, and vice versa.
The constant stare down across space. What's Charon like? Is it as active as Pluto?
New Horizons showed Charon's surface is also frigid, covered primarily in water ice, maybe with some ammonia compounds mixed in, but it appears to be much older and significantly less geologically active than Pluto's surface. More heavily cratered, fewer signs of recent resurfacing, though it does have some massive canyons suggesting past tectonic stresses. It's a different world, despite being so close.
Interesting contrast. What about the smaller moons? Nix, Hydra, Kerberos, Styx. Are they just tiny rocks?
They are small and irregularly shaped, yes, like captured asteroids almost, but their orbits are surprisingly ordered, nearly circular, nearly in the same plane as Charon's orbit, and locked in complex resonances with Charon. It's a very tidy system, which is part of the puzzle of their origin.
Did New Horizons give us any clues about other, as yet undiscovered moons? Or maybe even rings, like Saturn or Jupiter have? Did it look...
It looked very carefully. The New Horizons spacecraft conducted an extensive search for other regular moons, larger than about 1.7 kilometers in diameter, but found none. This suggests that if there are any others hiding in the system, they must be exceedingly small.
So probably no big surprises left there.
Probably not in terms of large moons. While even smally moons, maybe just 1 to 2 kilometers across, could theoretically exist and remain dynamically stable in certain regions, finding them is tough. Perhaps future observations with the James Webb Space Telescope might help constrain the masses of the known small moons or potentially reveal even fainter, unknown ones.
And rings. Did it find any hint of rings?
New Horizons also searched very carefully for rings, anything comparable to the faint rings around Jupiter or Uranus, let alone Saturn's glories, but observed no such structures around Pluto at all. The system appears remarkably dust-free and quite compact gravitationally. It seems Pluto and Charon have tidied up their neighborhood pretty effectively over billions of years, even if not quite enough to meet the IAU definition.
Good point. Okay, it's amazing how much we've learned about this complex system, from its potentially violent birth to its dynamic present. Now let's inevitably move into the Great Debate, specifically addressing Pluto's demotion, a shift in planetary understanding. Because let's face it, for generations of us growing up, Pluto was simply the 9th planet, an immutable fact etched into textbooks in our minds.
It absolutely was, no question about it. Discovered in 1930 by the American astronomer Clyde Tombaugh at Lowell Observatory.
Right, a young guy then.
Very young, yeah. Pluto was immediately classified as the 9th planet in our solar system, and its designation as a full-fledged planet shaped generations of textbooks, classroom models, those mnemonic devices we all learn.
My very excellent mother just served us 9 pizzas. Pickles.
Pizzas, usually, yes. It shaped public understanding of our cosmic neighborhood for over 75 years. It truly held a special place in our solar system map.
But then came that fateful day, August 24, 2006. That marked a really significant turning point, didn't it? A controversial one.
It did, and it sent ripples, maybe even shockwaves, through both the scientific community and the public consciousness. On that day, the International Astronomical Union, the IAU, which is the globally recognized authority for naming celestial objects and defining astronomical classifications, formally voted to reclassify Pluto as a dwarf planet.
And this wasn't out of the blue, right? This decision capped years of debate simmering among astronomers.
Absolutely. Years of scholarly debate, primarily sparked by the accelerating discovery of other large objects out in the Kuiper Belt, that region beyond Neptune where Pluto lives. The real trigger was the discovery of Eris in 2003.
Eris. What was special about Eris?
Eris was found to be similar in size to Pluto, maybe even slightly smaller in diameter, but actually about 27% more massive.
More massive than Pluto.
Yeah. Eris's discovery really forced the issue. It posed the question. If Eris exists, and it's more massive than Pluto, does that make Eris the 10th planet? And if Eris is a planet, then what about other recently discovered large Kuiper Belt objects like Haumea and Makemake? Are they planets too? How many more planets were we going to have to memorize? The list threatened to grow very long.
Right. You could just keep adding planets indefinitely without some kind of clear definition. So to avoid an endless list, the IAU felt they needed objective, physical criteria. What were the official criteria they established for a celestial body to be considered a planet in our solar system?
They established three specific criteria that an object must meet. First, and perhaps the most obvious, it must orbit the sun directly, not another planet.
Okay, simple enough. Moons are out.
Right. Second, it must have sufficient mass for its self-gravity to overcome its internal rigid body forces so that it assumes a hydrostatic equilibrium.
Hydrostatic equilibrium. That just means it has to be round, right?
Basically, yes. It must be massive enough for its own gravity to pull it into a nearly round or spherical shape, smoothing out any major irregular lumps and bumps over time. Think of it like a giant blob of dough that's so big and soft, its own weight pulls it into a near-perfect sphere. Little asteroids are lumpy, big planets are round.
Okay, orbits the sun is round. What's the third one? The controversial one.
The third one, and this is indeed the crucial point for Pluto, is that it must have cleared the neighborhood around its orbit.
Cleared the neighborhood. And this is where Pluto ran into trouble, correct? It's the sticking point for its planetary status, the reason for the demotion.
Exactly. Pluto comfortably meets the first two criteria. It definitely orbits the sun, and it's certainly massive enough to be pulled into a nearly round shape by its own gravity. We saw that clearly with New Horizons. However, it unequivocally fails the third criterion because it has not cleared the neighborhood around its orbit.
What does cleared the neighborhood actually mean in this context? Does it have to be completely empty?
It doesn't mean perfectly empty, no. It implies that the object has become gravitationally dominant in its orbital zone over the age of the solar system. It's either accreted, absorbed, or gravitationally ejected most other smaller bodies that share or cross its orbital path. Pluto, however, shares its orbital region, the Kuiper Belt, with many other celestial bodies, some of similar sizes like Eris, Haumea, Makemake, and countless smaller ones. It hasn't dominated its zone.
So it lives in a crowded neighborhood, essentially.
A very crowded neighborhood, and this is a key distinguishing factor from the 8 classical planets, like Jupiter or Earth or Neptune. They have gravitationally dominated their orbital zones over billions of years, sweeping up or flinging away most of the other significant objects, leaving their paths relatively clear of comparable bodies.
Okay, I see the distinction. And that's how the dwarf planet category was officially born, providing a new classification home for objects like Pluto that met some but not all criteria.
Yes, exactly. The IAU formally defined a dwarf planet as a celestial body that meets the first two criteria. It orbits the sun and is nearly round, but not the third criterion of having cleared its orbit. It's a specific category. This new category currently includes Pluto, Eris, Haumea, Makemake out in the Kuiper Belt, and also Ceres, the largest object in the asteroid belt between Mars and Jupiter. And potentially, hundreds more dwarf planets might be identified in the Kuiper Belt as we discover and study more objects. It brought a form of logical order to the classification chaos caused by the new discoveries, but yes, at the cost of Pluto's historical planetary status.
Even with that clear, albeit controversial definition from the IAU, the debate absolutely continues to this day, doesn't it? Especially among planetary scientists themselves. Let's delve into the enduring controversy: science, identity, and definition. What are the main arguments for Pluto retaining its planet status, or maybe for using a different definition of planet altogether?
Oh, the arguments are quite compelling for many planetary scientists, particularly those who actually study the physical nature of these objects, the geologists, the atmospheric scientists. Many, including very prominently Alan Stern, the principal investigator of NASA's New Horizons mission.
Right, he's been very vocal.
Very vocal, yes. They argue vociferously for a definition of planet based primarily on a body's intrinsic qualities. They believe planehood should be defined by what the object is physically and geologically, for example, being large enough to be round due to its own gravity and not being a star, not undergoing nuclear fusion, rather than being defined by external orbital factors like where it is or what other objects happen to be nearby.
So it's about the object itself, its internal characteristics, its geology, its atmosphere, not about its location or its gravitational influence on its surroundings. That makes intuitive sense from a what is this thing perspective.
Precisely. It's a geophysical definition versus a dynamical one. These scientists point out, quite reasonably, that planetary geologists routinely refer to large, geologically active moons like Saturn's Titan and Jupiter's Europa as planets or worlds in their research papers and discussions, even though they orbit another planet, not the sun directly, and certainly haven't cleared their own orbits around their parent planet.
It's true. We talk about oceans on Europa, methane lakes on Titan. They feel like planets in many ways.
They do. Which indicates, Stern and others argue, that the IAU's clearing the neighborhood criterion is simply not functionally useful or even relevant in their specific field of study when they're comparing the physical processes on these diverse worlds. Advocates for Pluto's planetary status also strongly highlight its incredible geological complexity, which New Horizons revealed in stunning detail. They often say it's more dynamic and alive than Mars, geologically speaking.
Wow, more active than Mars.
In some ways, yes, with only Earth and perhaps a few other active bodies like Io or Triton possessing arguably more complex and varied ongoing geology. To them, a body with vast nitrogen glaciers actively flowing, towering cryovolcanoes that might still be erupting, a complex layered atmosphere, and a potential subsurface ocean must be considered a planet regardless of what else is floating around in its orbital zip code. Its intrinsic nature screams planet.
Okay, that's a strong case based on geology. And the clearing its orbit rule itself, Criterion 3, has faced significant criticism from various corners of the scientific community, even beyond the pro-Pluto camp. What are the main points of contention with that specific rule?
Yes, the clearing its orbit rule has been intensely debated and criticized on several grounds. Some argue that if you take clearing its orbit absolutely literally, then no planet truly clears its orbit entirely. Earth, for example, shares its orbit with thousands of near-Earth asteroids and other debris. Jupiter shepherds entire swarms of Trojan asteroids in its orbit.
So if we apply the rule with absolute strictness, even Earth might not technically qualify.
That's the argument some make, yeah. It suggests the definition itself might be inherently fuzzy or problematic if pushed to its logical extreme. Others contend that the historical division between planets and asteroids, going way back, was originally based more on how these bodies formed and whether they grew large enough to become round, not primarily on whether they had gravitationally dominated their orbital regions later on. They see the IAU definition as imposing a new ahistorical criterion.
And isn't there also a philosophical angle? Something about different definitions being useful for different purposes.
Yes, exactly. There's a perspective sometimes called planet pluralism. This idea suggests that maybe there isn't one single correct definition of planet. Instead, there could be multiple equally legitimate definitions, each useful for different scientific subfields.
Like geologists use one definition, orbital dynamicists use another.
Precisely. Planetary geologists, focused on the body itself, might prioritize intrinsic properties like roundness and geology. Orbital dynamicists, focused on the structure and evolution of the solar system, might prioritize orbital characteristics like clearing the neighborhood. The idea is that different definitions serve different, valid scientific purposes, and we don't necessarily need to force one definition onto all contexts.
So this whole controversy, it really isn't just about semantics or labels, is it? It sounds like it taps into a deeper philosophical discussion within science itself, about how we categorize and define reality when it's complex.
It absolutely is, and that's a brilliant way to frame it. The controversy over Pluto's status is much more than just arguing about words. It reflects a deeper planet problem in the philosophy of science. It draws striking parallels to the long-standing species problem in biology. How do we define what a distinct species is when evolution is a continuous process with fuzzy boundaries?
Right, where do you draw the line?
Exactly. It highlights fundamental questions about how scientists categorize and define natural kinds. Can or should a scientific definition change over time as new discoveries come to light? Can it legitimately include relational properties, like clearing its orbit, which depends on other objects, or historical properties, how it formed or evolved, or should it only be based on intrinsic current properties? Can a definition admit vague boundaries or borderline cases and still be scientifically useful? The Pluto debate is a fascinating, real-world, ongoing example of science grappling with these deep philosophical questions about classification itself.
And this debate, this scientific and philosophical discussion, clearly struck a massive chord with the public. I vividly remember the outcry, the Save Pluto campaigns, the internet memes, the genuine sadness many people felt for Pluto losing its status.
Oh, without a doubt. The public reaction was intense and widespread. Pluto's demotion sparked not just debate, but real, palpable emotional attachment. Many people felt a profound sense of loss for the ninth planet they had grown up with, learned about in school, built models of. It had become deeply ingrained in the cultural identity of the solar system for generations.
Yeah, it felt personal somehow.
It did. Social media movements like Facebook groups titled "When I Was Your Age, Pluto Was a Planet" garnered millions of members almost overnight. It really showcased how Pluto, perhaps more than any other planet besides Earth, had become a cherished part of our collective childhoods and popular imagination. And despite the formal scientific reclassification by the IAU, the idea of Pluto as a planet persists strongly in popular culture and everyday conversation even today. It underscores the sometimes significant gap between precise scientific definitions and common understanding or cultural inertia.
It truly demonstrates how science, when it evolves and changes classifications, can intersect with deeply held societal beliefs and even powerful emotional connections. It's a powerful reminder of how ingrained some scientific facts become in our culture and how challenging it can be to update them, even when the science moves on.
A real lesson in science communication and cultural impact, for sure.
It's fascinating how a scientific reclassification can become such a huge cultural moment. Okay, let's pivot now towards the end here, focusing on Pluto's enduring relevance, exploring its ongoing practical relevance and broader implications. First, how does Pluto, despite its distance and its contested status, still act as a crucial gateway to the outer solar system? Why is it still so important?
Well, going back to its discovery, Pluto, found in 1930, was much more than just a new, faint dot in the sky. It was the very first trans-Neptunian object, or TNO, ever identified. It was the first hint of a vast population beyond Neptune. Its discovery literally opened the door, a cosmic portal, to understanding a huge, previously unknown region of our solar system, a third zone beyond the terrestrial planets and gas giants, a region we now call the Kuiper Belt. Before Pluto, we really didn't know this immense reservoir of icy bodies even existed out there.
And now we know that region is just teeming with objects, right? Like a cosmic archaeological site preserving the early solar system.
Exactly. Today, over 5,000 TNOs have been officially identified and cataloged, and literally thousands more are suspected to exist, maybe millions of smaller ones. Studying their orbits, their compositions, their distributions provides crucial insights into the early architecture of our solar system.
How so? What do they tell us?
Well, their current orbits, especially the patterns we see, strongly support the idea that the giant planets, Jupiter, Saturn, Uranus, and particularly Neptune, didn't form where they are today. They migrated significantly in the early solar system. Computer models show that as Uranus and Neptune likely migrated outward, their gravity gravitationally scattered and ejected many smaller icy bodies, while capturing others into resonances, sculpting the complex structure of the Kuiper Belt orbits we observe today.
So these distant TNOs are like cosmic fossils. They preserve the evidence of those giant planet migrations billions of years ago.
Precisely. They are like the scattered remnants of that dynamic era, telling us a story of massive planetary migrations and the gravitational shaping of our entire solar system.
And some of them are even more pristine than others, right? Like untouched building blocks.
Yes. Of particular interest are the dynamically cold classical TNOs. These are objects that have very low inclination, meaning their orbits are very flat, lying close to the main plane of the solar system, and low eccentricity, meaning their orbits are nearly circular. They haven't been significantly disturbed or scattered.
So they're still where they formed.
That's the thinking. These cold classicals are thought to still occupy orbits very close to their primordial formation locations. They somehow avoided being significantly disturbed by Neptune's migration. They represent relatively undisturbed remnants, essentially, pristine building blocks from the original protoplanetary disk from which our entire solar system formed 4.5 billion years ago. Arrokoth, that snowman-shaped TNO visited by New Horizons after Pluto.
Right, the contact binary.
Exactly. Arrokoth is one such spectacular example. It looks like two planetesimals that gently bumped together and stuck. It gives us an incredible direct window into the very initial accretion process, how planets started forming from these small building blocks.
And now the James Webb Space Telescope is joining the search out there, right? What's its specific role in continuing to unravel the secrets of this distant, pristine Kuiper Belt region?
JWST is a total game changer for studying TNOs, yeah. It's a truly powerful new tool, complementing and extending the incredible discoveries made by the New Horizons flyby. While New Horizons gave us that incredibly detailed close-up snapshot of Pluto, Charon, and Arrokoth, JWST provides unparalleled sensitivity and spectral capabilities to study a much wider range of TNOs from afar.
What can it do that we couldn't before?
Well, it can make the first ever detailed spectral observations of some of the most distant and faint extreme TNOs objects like Sedna, whose orbits reach incredibly far out, almost into the Oort cloud or interstellar space. Studying their surface composition with JWST's infrared eyes can tell us about conditions in the outermost reaches of the protoplanetary disk.
And what about binaries like Pluto-Charon?
JWST can also conduct high-resolution imaging and spectroscopy of numerous other TNO binary systems. This will help us better understand the origins of their satellites. Were they formed by giant impacts like possibly Pluto Charon, or did they co-form, or were they captured? By studying the compositions and orbits of many binary pairs, we can test those formation theories more broadly. These new observations from JWST are expected to yield a torrent of new ideas and discoveries about the early solar system, continuing to refine our understanding of its deep history, all sparked originally by the discovery of Pluto.
It's amazing. From the formation of our entire solar system to, maybe, the possibility of life itself, Pluto seems to touch on some truly profound questions. Let's explore that final angle. Implications for life and habitability. The subsurface ocean potential. It still feels hard to imagine life on a frigid world like Pluto, so incredibly far from the warmth and light of the sun.
It does, at first glance, seem like one of philanthropical least likely places. But that's where our scientific understanding, particularly about internal heating and the potential for liquid water, has dramatically shifted in recent decades, not just for Pluto, but for icy moons across the outer solar system.
Because of that internal heat source.
Exactly. Despite its extreme distance from the sun, Pluto undoubtedly possesses that internal energy source. The slow, steady radioactive decay within its substantial rocky interior, as we discussed. This heat, though generated slowly over billions of years, appears sufficient to warm the interior rocks close to their melting point, creating an environment deep beneath the ice shell where liquid water is not just a wild fantasy.
So similar to what we discussed about its differentiation process requiring melt, this ongoing internal heat could keep water liquid today. Is a liquid water ocean considered a real possibility, not just theoretical speculation?
It is considered a very real possibility, yes. Given Pluto's bulk composition, roughly 2/3 rock, 1/3 ice, and its demonstrated internal heating, evidenced by its geology, scientists now strongly believe there's a distinct possibility, maybe even a likelihood, of a substantial subsurface ocean beneath its kilometers-thick ice shell, perhaps hundreds of kilometers deep.
Wow. And the ammonia helps keep it liquid.
And remember that crucial ingredient, the likely presence of ammonia mixed in with the water, acting as that natural antifreeze. As we noted, even small amounts significantly depress the freezing point of water down to maybe 176 Kelvin or so. This greatly aids in maintaining a liquid layer for potentially billions of years, even in Pluto's incredibly frigid environment.
Okay, so we have internal heat from radioactive decay, potentially liquid water, and ammonia antifreeze. That certainly raises the tantalizing question of habitability far beyond the traditional Goldilocks zone around a star.
It absolutely does, and it's radically pushing the boundaries of our search for life in the universe. While direct, conclusive evidence of a current ocean is still needed, perhaps future missions could detect it with radar or magnetic field measurements. The strong potential for internal heat and long-lived liquid water raises fascinating questions about Pluto's potential habitability.
Habitable how? What kind of life could exist there?
Well, scientists are actively exploring whether the radioactive decay within Pluto's rocky core could drive the kind of chemical interactions between water and water-rock interactions that we see at Earth's mid-ocean ridges, those deep-sea hydrothermal vents.
Right, the black smokers that support whole ecosystems without sunlight.
Exactly. On Earth, these vents support thriving ecosystems entirely independent of sunlight, based on chemosynthesis life deriving energy from chemical reactions rather than photosynthesis. Could similar chemical energy sources exist at the base of Pluto's potential ocean, where water meets the warm, rocky core? Could that potentially support some form of microbial life, however rudimentary? It's a profound question that Pluto, this tiny, distant world, now forces us to seriously consider.
And again, this potential ocean, its very existence today, ties back directly to Pluto's very origin story, doesn't it? It's like a cosmic loop connecting the beginning to the present potential for life.
Yes, it's a direct and critical link, beautifully highlighting how new observations and modeling about current conditions can refine, constrain, or even challenge our fundamental understanding of planetary origins billions of years ago. For example, as we touched on, definitive evidence of a substantial subsurface ocean on Pluto today might actually argue against certain formation scenarios, like the kiss and capture model, if that model implies a colder start.
Right, because a colder start makes it harder to keep an ocean liquid for so long.
Exactly. So if a significant ocean is confirmed in the future, it might lend more weight to models involving a hotter start, like a more energetic giant impact, or perhaps a more gradual accretion process that trapped more heat. It's this continuous process of scientific refinement, where new data forces us to reevaluate our long-held theories about everything from formation to habitability.
This entire deep dive really has been a powerful testament to the enduring value of space exploration and scientific inquiry. The New Horizons mission in particular just perfectly exemplifies this, doesn't it?
It truly does. Missions like New Horizons fundamentally transform our understanding of distant worlds in ways we can barely even imagine beforehand. Think about it. Before July 2015, Pluto was just a fuzzy blob in even our best telescopes, a cold, distant mystery,
A point of light.
a point of light. Mere hours after the flyby, it became a crisp, colorful, stunningly complex geological world with vast heart-shaped glaciers, soaring ice mountains, blue skies, and even evidence of ongoing cryovolcanism. This monumental shift in perception from blurry dot to real world exemplifies precisely why we explore, why we go to space. To learn about the universe around us, to push the boundaries of knowledge, to understand our own origins, and ultimately to improve our existence and our perspective on our place in the cosmos.
It's clearly more than just gathering scientific data, isn't it? There's a profound inspirational aspect that often transcends the pure science itself.
Absolutely. Space exploration, at its best, is a unifying, borderless human endeavor. It provides invaluable new, objective perspectives to study our own planet Earth and the solar system. It drives technological advancements that improve our daily lives in countless, often unexpected ways, from medical imaging to computing to materials science. And perhaps most importantly in the long run, it inspires new generations of artists, thinkers, engineers, and scientists. It pushes the boundaries of human ingenuity and encourages us all to dream bigger, to look up.
Like those iconic images from Voyager's, especially the pale blue dot photo. That single picture really changed how many people viewed Earth and our place in the vastness of space, didn't it?
Without question. The Voyager missions, and especially iconic images like the pale blue dot, captured by Voyager 1 from billions of miles away, looking back at Earth as a tiny speck, those profoundly influenced popular culture and fundamentally shifted our perception of humanity's place, our fragility, our interconnectedness in the cosmos. New Horizons discoveries at Pluto, much like Voyager's grand tour decades earlier, continue this powerful legacy. They help us understand Earth's unique position, its incredible geological activity compared to some worlds, its precious capacity to sustain life. Seeing other worlds, even those as distant, alien, and seemingly hostile as Pluto, gives us a profound perspective on our own planet, reminding us just how special and unique our own pale blue dot truly is.
And finally, thinking back to the classification debate, the Pluto debate itself, messy as it was, has actually been a powerful living lesson in how science works, hasn't it? A reminder that it's a dynamic, evolving process, not a static book of facts.
It truly has. That whole debate, frustrating as it might have been for some, is a powerful, real-world lesson in the very nature of science. It's not static, it's not a fixed set of unchanging facts carved in stone. It's an evolving process where definitions change, classifications are refined, and understanding deepens as new discoveries are made. It's all about adapting our understanding based on new evidence, even if that evidence challenges cherished notions, historical precedents, or deep emotional attachments.
Yeah, letting the evidence lead, even if it's uncomfortable.
Exactly. The fact that the scientific community, through the IAU, chose to grapple with the definition and redefine planet rather than just arbitrarily add potentially hundreds more objects to the list, rendering the term almost meaningless, demonstrates a commitment to maintaining precise classification and a coherent scientific framework, even if the process was contentious. It shows that science is a living, breathing body of knowledge, constantly being refined by new observations and deeper understanding. It reminds us that even when we think we know something, there's always more to discover, more connections to make, and certainly more questions to ask about the universe and our place within it. Pluto, perhaps more than any other object recently, has forced us to do just that.
What an incredible journey. From discovery to demotion to revealing itself as this complex, active world. After this whole deep dive, what stands out to you personally as the single most surprising or profound thing we've learned about Pluto?
That's tough. But maybe just the sheer, unexpected level of geological activity. The idea of nitrogen glaciers flowing, potential cryovolcanoes, on something so small and so far from the sun, it just shattered expectations about where geology ends in the solar system. It really makes you wonder what else is hiding out there in the Kuiper Belt.
Absolutely. A reminder that the universe is always stranger and more wonderful than we imagine.
Well said.
Thanks for listening to All in All.